generation, which involves the topic, intermediate languages, graphical representations, three-address code, quadruples, and triples. This slide shows different phases of compilation. As we know, the first phase is lexical analyzer, which receives the source program as its input, and it will be converted into a sequence of tokens. This sequence of tokens will be received by the next phase, index analyzer, where it check whether the syntax of the program is correct or not by constructing a parse tree, and this parse tree will be given as input to the next phase, semantic analyzer. The output from the semantic analyzer will be an annotated parse tree, and which will be received by the next phase, intermediate code generator. The output of this intermediate code generator is nothing but an intermediate form or intermediate code or an intermediate representation, which will be given as input to the next phase, code optimize. In the phases of compilation process, the first four phases can be combinedly called as front end of the compiler, and the remaining two phases or the last two phases, code optimizer and code generator, can be combinedly called as the back end of the compiler. So this intermediate code is actually the output of the front end, which will be received by the back end, and from this intermediate code, the back end of the compiler will generate the target code. This intermediate code can be also called as intermediate representation or IR. The two important things which should be kept in mind while designing an intermediate code are: the IC generation process should not be very complex, and it should not be difficult to produce the target code from the intermediate code. So we have different types of intermediate representation. The first one is high level representation and second one is low level representation. High level representation means here the representation or the intermediate code is closer to the source language, and this is quite easy to generate from the input program, but code optimization may not be straightforward because it actually depends on the machine features. Now the low level representation, this is closer to the target machine, definitely so suitable for register allocation and instruction selection, easier for optimization, final code generation. This slide shows the different forms of intermediate representation. The four important forms are syntax tree, direct acyclic graph or DAG, postfix notation, and three-address code. The first among them is nothing but syntax tree or abstract syntax tree. This is actually a graphical intermediate representation. This depicts the hierarchical structure of a source program. See, consider the example 3 into 5 plus 4. Let it be an input expression, and the grammar shown is given. Shown in the slide is given. Then the parse tree corresponding to this expression 3 into 5 plus 4 based on this grammar is also shown. So the parse tree actually shows the different steps which is involved in the parsing process. Nothing but see, whenever I am seeing this input 3, it will be first of all reduced to this digit, then this digit will be reduced to F will be reduced to T. So similarly this 5 will be reduced to digit will be reduced to F, and whenever it is T into F, by using this production I can convert this T into F, or I can reduce this T into F to T. So this entire parsing process is shown in this parse tree. Okay, but in the case of syntax tree, only the leaf nodes and the operator nodes and the operand nodes are present in the syntax tree. For example, for the expression 3 into 5 plus 4, the syntax tree will be 3 into 5 plus 4. Not any grammar symbols or anything like that is represented. Only the operands and operator will be present in the syntax tree. So we can call that abstract syntax tree, or syntax tree is a condensed form of parse tree which is useful for representing the language construct. Then constructing syntax tree for an expression, we have actually three different functions can be used for the constructing the syntax tree from an expression. The first function is make node, which is nothing but a function which is used to construct the node operator nodes. And we have two make leaf functions. One is for the construction of the identifier nodes, and the second one is for the construction of numbered nodes. Okay, number leaf nodes. So the first function is make note. The arguments received by this make note functions are op, left and right. So this op is nothing but the operator, and left and right are its operands. Okay, the pointers to its operands. Then the make leave function, the first one, make leave id comma entry, which is nothing but an leaf is actually a function to construct the leaf node for an identifier. Then the entry will be the corresponding pointer to the symbol table entry. Then make leaf num comma val is nothing but an function which is used to construct a number leaf node, for the val will be the value of that number. And all these functions return a pointer to a newly created node. So consider an example. Expression a minus 4 plus c. So suppose for this a minus 4 plus c, here I am showing the different steps or the different functions which is used for the construction of the syntax tree. First of all, for the leaf node a, we have to construct, we have to call the function mk leaf, that is make leaf id comma entry a. So when I am calling this function make leaf id comma entry a, then definitely a node like this will be created id. So this function is actually used to construct this this leaf node id, and this is entry a means this is actually the entry for a in the symbol table. And this, when I'm calling this function, it will return a pointer, and let me represent it with p1. Okay, so next I have to construct the node for this 4, not for this number 4. So for this I am calling the function make leaf num comma 4. Make leaf num comma 4. So when I am calling such a function, then this number leaf node will be constructed. Okay, and it will be return a pointer like p2. Okay, so now I have to construct this node for this operator minus. So for this I am constructing the, I am calling the function mk node minus p1 p2. So when I am calling such a function, a node like this will be created. Make node minus is actually the operator, its operands are p1 and p2. Then coming to the next thing, I have to create the node corresponding to this c. So definitely I have to call the function make leaf. So make leaf id comma entry c will helps me to create a node like this, and this entry for c will be the pointer to the symbol table. And then I have to construct the node corresponding to this plus. So I have to call this make node plus p3 and the p4, which means p3 is actually the pointer to this one, and p4 is the pointer to this. P4 is the pointer to this make leaf. So after the sequence of functions, after calling the sequence of functions, it's possible for me to construct the syntax tree corresponding to the expression. So now we are discussing about how the syntax tree can be actually stored in the memory. We can use two methods. Either we can go for a tree-like representation or a tabular representation. So to differentiate between these two representations, I am going to use this example: a equal to b into minus c plus b into minus c. So the syntax tree corresponding to this expression will be a equal to, or either you can write it as assign, or you can just use the operator equal to. A equal to b into a equal to b into minus minus c plus b into minus c. Okay, and it will be assigned to e. So the syntax tree corresponding to this expression will be like this. Then we can either go for a tree-like representation, or we can go for a tabular representation. See, the tree-like representation is nothing but what we have discussed on previous slide, which means how to construct a syntax tree using the function. So if my expression is a equal to b into minus c plus b into minus c, first of all